let's go to the second topic of interest here. So the importance of the water matrix and the practical implications of that. Um, Actually, water matrix, or deciding if ozonation is a suitable technology for your site or for your matrix, it's much more than looking at bromide levels or DOC levels. There are some general guidances. For example, if you look at wastewater effluent and it has bromide higher than 150 or 100 micrograms per liter, you could say, well, there is some risk for bromate. If you're lower, you're safe. But we have seen plants where you have much higher levels and still limited bromate formation. So it really depends on not only on the DOC, it not only depends on your bromide, it depends on a lot of things. What are the other things? Examples are nitrites, ammonia, carbonates, temperature, pH. There are lots of things to say about this. We can have actually 5 webinars on each of those separately because there is simply a lot of chemistry involved. One example, this is actually a table from a recent paper co-authored by us and a couple of other folks from the US and also France. I think Heather, who is the first author here, this was a WebTech paper. She's also attending this webinar. But there's one table there. It is not a complete table, but it summarizes, okay, per variable, what is the impact on your system? Because some variables affect your ozone and hydroxyl radical levels, but other variables also affect the bromate formation mechanism as such. pH, for example, has an impact on all of them, on including bromate suppression strategies. Even if you dose peroxide to suppress bromate, pH has an impact. So it means if pH changes, all of these 3 things change simultaneously. And this is causing a lot of non-linear behavior, looking across plants, looking throughout time. But you can see that there are other variables of interest. Another example is alkalinity, which scavenges your radicals, right? Ammonia, for example, has a very, very big impact on bromate formation because it will scavenge part of your bromide to form monobromamine, actually. So this is, these are all things you have to understand. You don't have to know them by heart. They're all included in the model, but there is a lot of things going on. But to make it practical again, we will go back to Italy to our colleague and show a demo on this impact of the water matrix. So Giacomo, the floor is yours.
Yes, thank you. All right, let's go once more to the Sumo platform to have a look at what is the impact of a dynamic influence on your effluent chart. I mean, on your effluent bromate and your micropollutants conversion, for instance. So here you see the layout that Roberta just showed, and then here is a time a data set of the influent with the flow rate, with the UVA as an indication of the organics, dissolved organic carbon, ammonia, and nitrate. Then you also have the model gets also nitrite, alkalinity, and many other variables as an input. If they're not available in your case, don't worry, we deal with it. There is no problem. We can live with less variables. But what I want to show you here is the effect of highly fluctuant dynamics on the final effluent. What you see here is the flow rate with some rain events over 20 days. Let me continue the simulation because I stopped it for 1 second, then you can see it progressing. And then you have here the UVA absorbance of this influent that is coming into our installation, and the organic, dissolved organic carbon, ammonia fluctuation, and so on. So every one of these variables will have an impact on your final bromate formation and also on the micropollutants removal. So, and as details are important, then all of these variables will affect both the ozone lifetime, so the ozone residual in your in the installation, and will also then ultimately also affect the lifetime of radicals, because changing the water strength with the rain events, you can get dilution. Your radicals might live longer, your ozone might live longer, and you might end up with very high peaks of bromate form, like in this case, up to this is up to 25 micrograms per liter. And why this is occurring? This is different reasons counter-occurring at the same time, occurring at the same time. So what you see here as the residuals of ozone at the end of the installation, it means that at this point in time, there was a rain event or some dilution caused by different factors, which made the ozone dose in the system be excessive, because here we are just blowing without control a certain amount of gas in the 3 columns. We are splitting the dose, but we are not efficiently controlling the dose. So in this case, the dose of ozone might be excessive, and you get residuals. This low residuals, apparently not even measurable in an effluent, will affect the bromate formation and the whole installation. So this has an important effect in design. And what happens in the deeps? In the deeps, sometimes the presence of ammonia helps knocking down the bromate form, as Wim anticipated. But sometimes the sole ammonia presence is not enough, because the matrix composition does not make the life of ozone and radicals short enough. And then having residuals for a sufficiently long time in your installation makes the bromate forming. At the same time, what happens is it's very high. What you see here is very tremendous dynamics in your performance of micropollutants removal. You have here a 10 minutes frequency data set, so you have very high resolution data plotted here over a time of 20 days in the simulation. And then you can check the plant-wide variables to check how much is varying the ozone dose in your installation throughout time. But what you can notice here is how much the influent variability, the influent composition, the water metrics changes. Even though it's the same water source, the water matrix changes in a way affecting very much the ozone residual and the effectiveness of the ozone treatment. All right, then we can go back to the presentation.
Thanks, Giacomo, for the nice illustration of the full-scale plant dynamics. So Giacomo has actually shown this dynamics. So not a single plant is actually static, because everything is varying. Even drinking water has seasonal variations. So if you look at wastewater effluent, it has more diurnal and weekly variations. Or of course, precipitation, rain is very important. In drinking water, the seasonal variations are very important. For example, ammonia and nitrification things in surface waters are very impacting. So typically you have all these dynamics, and the most important ones are, of course, flow rate, dissolved carbon, and we all know if you have a certain installation designed and your flow rate decreases, but you still have the same ozone system in place, your bromate might also be affected. Go higher if you push lower flow rates or increase the HRT, the residence time in your plant. So, well, what we typically see in both drinking water, but also especially in wastewater effluent, is the high impact of ammonia. So if your upstream ammonia fluctuates, your bromate will fluctuate with it. Typically, this is not visible In practice, because typically you take very few samples, either it's a grab sample or, for example, a 24-hour composite sample, but there is no online sensor for bromate. So unless you really take grab samples every 10 minutes, you cannot really capture these peaks. But in the end, in any plant, you have the average bromate, which might be reasonable, but there are definitely bromate peaks. There is no doubt about that. They are caused by pH fluctuations, but ammonia is a very important one. We have seen in some plants an almost one-on-one relationship.